beginning, the navigator faced three problems. Where am I? Where is my destination? How do I get there safely? These were the questions he must answer or perish. Early men had dreams, magnificent dreams. Yet dreams alone were too fragile. The sky and space could only be conquered in myth and legend. But the sea was vulnerable. Its dangers and terrors were many, but so were its benefits. For a long while, sailors stayed in sight of the coast to observe the landmarks that gave them their location and direction. But the desire to achieve wealth and live to enjoy it led mariners to learn the sea's own pathways. To estimate their speed, to determine how deep the water was beneath their vessel, to know the behavior of wind, current, and tide. To learn which clouds indicated fair sailing, that although they could not see land, certain clouds could guide them to it. And they learned about the heavens. From Crete, from Greece, from Tyre and Sidon, with only the rudiments of navigational art, men set out to roll back the unknown and to make themselves rich. Oars crashed, iron cracked, rim struck on rim where the Vikings rode. The Atlantic coast of Europe, the Mediterranean, the Levant, all knew the dragon ship. But the destiny of these Vikings, these Normans, lay westward, in Britain and Ireland, in Iceland and Greenland, and in Vinland the Good. Those pioneer navigators who returned became the heroes of legends, of epics and sagas. They were a very small minority. Something was needed which could tell a sailor his way even in new and unknown seas, beneath unfamiliar skies, despite fog, clouds, and storm. Many methods for piercing nature's veils were tried. Many failed, but one did not. Soon this north-pointing needle was fastened to a paper disc, and the captains who used it could tell where the North Star lay and in what direction they were sailing, despite darkness or bad weather. But where was the destination? The only maps available gave but a rough idea of certain places that a man might like to reach. As waterborne commerce flourished, more detailed information was demanded. The location of coasts and harbors was more accurately shown on the new Portolan or harbor-finding charts. By combining information obtained from the compass, direction, and bearing, with the information given by Portolan charts, a mariner could, for the first time, plot a course from point to point. Dead reckoning had begun. But these charts, this type of navigation, were only helpful in a small, confined area, and the world was no longer small and confined. Fresh ideas and new techniques were demanded. The Renaissance was making men discoverers and explorers once again. One of these men, Prince Henry of Portugal, Henry the Navigator, dreamed of finding a sea route to the Indies. To develop methods for crossing unknown seas and mapping unknown lands, he established a school of navigation, the first of its kind. Here, the experiments of astronomer, mathematician, and cartographer were coordinated with the practical work of shipmaster and navigator. For the first time, theory and practice became partners. Henry's captains had the compass to give them direction. What they needed to know was position, the position of their ship, and the position of new, rich lands. On land, astronomers were able to determine latitude, the distance north or south of a given point, by measuring the angle between the horizon and the sun or the North Star, then correcting these measurements with the aid of pre-computed tables. With the astrolabe, an angle measuring instrument, the ordinary mariner had a fair idea of his latitude. But this was only half a solution. Without also being able to determine longitude, the distance east or west of a given point, there was not even a partially accurate way of fixing position. Nevertheless, most captains were sure of their position. Fortunately, Portugal's big interest was in north-south sailing, yet navigation and charting did become more accurate. This produced both results and envious neighbors. Spain wanted a share. So Ferdinand and Isabella decided to risk some $14,000 on an obscure but obstinate Genoese mariner who was sure that he could reach the east by sailing west, Columbus. His only navigational aids of any value were the ship's compass and a pair of dividers with which to mark off the estimated distance sailed each day. Yet this primitive dead reckoning helped Spain to create an empire and proclaimed the New World to an awakening Europe. In less than 50 years, more of the world had been made known to the West than in the previous 5,000 years. Magellan was able to sail completely around the world. And a Flemish cartographer, Gerardus Mercator, developed maps that reflected this newly discovered roundness. And suddenly the world was alive with other men of great vision. Copernicus, Galileo, Tycho Brahe, Johannes Kepler, Sir Isaac Newton. Their concepts would not only revolutionize navigation at sea, but also man's relationship to sky and space as well. But governments and merchants were more interested in practical results. The Netherlands of that day excelled in cartography, instrument making, and the indispensable sailing directions. The British developed the log and knotted line, which gave the first accurate measure of speed. The French produced nautical almanacs. Instruments to measure the position of the sun and stars were improved. But it was not until 1730 when the ideas behind these instruments were combined with telescope and mirror by Thomas Godfrey and John Hadley was really precise observation possible. With this new instrument, the sextant, the navigator could see both the horizon and the sun or star at the same time and move the object down from the sky until it seemed to touch the horizon. Then he could read its angular elevation in accurate terms. Most important, both the observed body and the horizon moved together. No longer could heavy seas, pitching and rolling, cause the former errors of several degrees which made captains miss their destinations. But the longitude at sea was still a mystery. Distraught governments offered tempting cash prizes to whoever should find it. Sir Isaac Newton was quick to reply, "I wasn't aware that it had ever been lost." He then went on to state both the problem and the solution. If an accurate clock could tell the navigator the correct time at some known meridian of longitude, say the Greenwich meridian, and he could determine the local time by measuring the position of the sun, then using tables and simple arithmetic, he could convert the difference between sun time and clock time into degrees, minutes, and seconds of longitude, and then into the number of miles he was east or west of the known meridian. But no clock made was good enough. The best scientific minds of Europe, Newton, Halley, Huygens, von Leibniz, were stopped. Perhaps it was only natural then that it took John Harrison, an uneducated Yorkshire carpenter, another 50 years to convince the academicians that the clocks which he invented, designed, and built met all of Newton's specifications. The final fundamental problem of marine navigation had been solved. With one of Harrison's chronometers and an accurate sextant, Captain James Cook's expeditions filled in the last major blank spaces on the map. Cook was killed in Hawaii in 1779. 4 years later, men flew for the first time. For the first few years, navigation was not the pilot's biggest problem. 120 years after man first left the ground, the Wright brothers made the first sustained flight in a motor-driven airplane. Average speed through the air, 31 miles per hour. Longest flight, 59 seconds. With the invention of the aeroplane, the navigator once again was faced with the same three problems. Where am I? Where is my destination? How do I get there safely? It took a war and another great age of exploration to get them to lift their eyes above the horizon. Lindbergh's solo flight to Paris finally converted public apathy for aviation into delirious enthusiasm. Real effort was concentrated on making the airplane a commercial success. And this would only be possible when it could keep to its schedules as regularly as trains and as accurately as ships. Some progress had already been made. The periodic compass, which was not affected by the airplane's movements and vibrations, was developed. Airspeed indicators and altimeters were in use. And there was a practical sextant for aerial use. Since the real horizon line was so far below the navigator and invisible at night, a bubble was substituted for it, permitting accurate celestial observation at any time or altitude in good weather. But the airplane moved at least 10 times as fast as a ship. This tremendous speed invalidated the navigator's calculations before they were even made. The airplane's movement in all three axes could be controlled when its attitude was known, but it couldn't always be known. And the wind was unpredictable. It could double your speed over the ground, or cut it to nothing, or make you drift miles off course. It all meant the same thing, a missed destination. To solve these problems, special techniques and equipment had to be devised. The drift meter showed the navigator how far off course the wind was forcing him, and in what direction to fly to counteract it. The directional gyro maintained a steady heading in all weather. Gyroscopic principles were also used as the basis for the turn and bank indicator. And the artificial horizon, which enabled a pilot to control the attitude of his plane when he could not see the real horizon. The great sensitivity of the aneroid, the heart of the common barometer, to changes in altitude was used in constructing a more accurate altimeter, as well as a rate of climb indicator. With instruments such as these, Jimmy Doolittle of the U.S. Army Air Corps was able to make the first completely blind landings. Man could now defy nature, but with the rapid developments in electronics, he began to dominate it. The U.S. government set up a network of radio beacons along the country's major airline routes. By riding the radio beam and making use of his blind flight instruments, the navigator could both read his course and calculate his position. During World War II, radar was developed and became an important detection device. It enabled pilots to know their ground speed and wind drift exactly. That is, by measuring the difference in frequency in a radar signal between time sent and time reflected back. Radar also took the dangerous element of blindness out of instrument landings. Compasses and direction-finding equipment were improved and refined, and the sextant had evolved into the automatic star tracker. Hyperbolic navigation, LORAN, DECA, and console permitted accurate position finding and course plotting over vast distances, even when no celestial sights could be taken. But there was another legacy of the war. The means to conquer the most remote, the most formidable part of our environment. The vehicle and the power to travel from the Earth to the planets. But the vehicle and the power must be guided. But the same questions remained. Where am I? Where is my destination? How do I get there safely? New problems complicated these questions. Space was a new world, and so was space navigation. It was no longer enough to know where man wanted to go. Now man also had to know where his destination would be when he intended to arrive. And before starting home, man had to determine to which positions both his destination and his home base had moved during his stay. His course was no longer a straight line on a map, but a precise orbit. In theory, there were an infinite number of these orbital paths which he might select. The trick was to find the orbital path that would give him the minimum danger of missing his goal completely, and running out of fuel and being trapped in space forever. And an error of just 1 foot per second in entering this correct orbit could cause him to miss his goal by tens of thousands of miles. Considerations of weight and space reduce the amount of fuel capacity available for making course corrections. Newer, stricter standards of accuracy and reliability, impossible to achieve a few years ago, were imposed and maintained. The navigation system which was selected was called Inertial Guidance. It was already being used in military aircraft. Today's hottest aircraft on which the free world depends, the Lockheed F-104G Starfighter in 9 of NATO's air forces, the McDonnell F-4C, the General Dynamics F-111, all depend on Lytton Industries built inertial navigation systems. Such systems ensure precise location fixes at supersonic speeds. And in war, the system would not betray the aircraft's presence or location. By measuring a vehicle's acceleration, the inertial system's computer can calculate the position and velocity of this vehicle at every instant of time. In a spacecraft's inertial navigator, 3 tiny accelerometers are mounted on a gyro-stabilized platform which maintains a fixed spatial orientation regardless of what the spacecraft does. They measure the direction and speed of each and every movement which the spacecraft makes. They continuously feed this information to the computer, which compares the craft's actual performance with the desired performance several times a second. The computer then uses the difference between the two to steer the spacecraft. At the exact instant when the craft is on an Earth parking orbit, the system turns off the rocket power and the vehicle takes up its orbital path around the Earth. At the proper predetermined time, the engine starts again, thrusting the craft into another larger orbit, which will bring it close to its destination. Using data, the computer immediately tells the crew how far off course they are and decides what corrections to make to bring them to their destination with a minimum use of fuel. When they arrive, the computer calculates the proper corrections to place the craft in another parking orbit and then onto a descent trajectory. But space is not the only area in which the new techniques have revolutionized the art and science of navigation. The computerized inertial navigation system itself, in one of its many forms, is just as useful on Earth as in space. It does not need to see or hear anything from the outside world, nor send out signals, so it cannot betray its presence or location, and it is independent of the weather and other external conditions. Submarines such as the Nautilus use it to make undersea voyages lasting for days, even months, and still find their destinations with extreme accuracy. When it is used together with an automatic star tracker to control its mechanical errors and verify its conclusions regarding position, and a Doppler radar system to give it exact information about ground speed and wind drift, it becomes, at least for the present, the ultimate navigational instrument. In the future, such instruments may provide the accuracy and rapidity of calculation needed to make the supersonic airliner a practical reality. But even these highly advanced tools and techniques do not mark the end of man's search for better means of finding his way. Navigation systems incorporating advanced microcircuits are in production, saving space and improving reliability. Horizon sensors that will pierce the clouds. Orbiting satellites that will broadcast continuous navigational information, control air traffic, and assist in search and rescue operations. These and other techniques will gradually become commonplace as man sets ever more precise goals for himself. Probably they would surpass the understanding of many of the hundreds and thousands of navigators, scientists, and engineers whose dedicated work in ages past led directly to their discovery and use. But our predecessors would recognize the key element, It is the same now as it was when some nameless ancestor first ventured onto the water on a log or a bundle of rushes. If man is to one day know the Milky Way, or see a galaxy as if it were a far-off country, a grouping of stellar states, of all the categories of knowledge he must acquire, a key one will be in the area of navigation.